Hello, a great welcome to the series on machine foundations. So this is lecture 4 of the series. So in this video, we will discuss on the analysis of damped free vibrations. So let us start the series. Okay, we know that from the basics that the dynamic equation of equilibrium for a single degree of freedom system is given by m into u double dot plus c into u dot plus ku is equal to ft. Now, as I told you, in this series, we are going to analyze the response of free damped vibrations, which means that in this general equation for equilibrium, we have to set only Ft equal to 0 because we have C inherent in the system indicative of a damped behavior, which means that for a damped free vibration, the equation of equilibrium, that is the dynamic, reduces to m into u double dot plus c into u dot plus ku equal to 0. So this is the linear homogeneous differential equation which we need to solve for obtaining the response u. Okay, fine. So let us normalize this differential equation with the mass m, which means that we need to divide every term by the mass m. And this provides us the equation u double dot plus c by m into u dot plus k by m into u equal to 0. Now let us introduce the following two terms. One term is familiar to us and the other one is already a new term, that is a damping ratio. So we introduce a new term, damping ratio, represented by the Greek letter C, that is equal to damping of the system divided by critical damping CCR, that is equal to C divided by, for the critical damping we make a substitution 2m into omega n. We will of course discuss the implication of the damping ratio C as well as the critical damping CCR onto the response of the system in the coming pages. So means that here we have the damping ratio C, which is C divided by 2m into omega n. Now the second substitution is already known to us, that is a k by m, it is omega n square. What is k by m? We know that it is nothing but it is the natural frequency of an undamped system, which means that making the substitutions, the differential equation reduces to u double dot plus 2c into omega n into u dot plus omega n square u equal to 0. Now let us assume a solution for the response u of the form that is already introduced in the previous videos also, u equal to a into e raised to st. Now let us differentiate the term u two times to obtain the velocity u dot as a into s into e raised to st and the acceleration u double dot as a into s square into e raised to st. Now let us substituting the values of u dot and u double dot in this equation. We obtain the equilibrium equation as a into e raised to st into s square plus 2c into omega n into s plus omega n square equal to 0. Obviously we know that a into e raised to st can be 0 or s square plus 2c into omega n s plus omega n square equal to 0. But the relevant solution will exist for a characteristic equation in S, which is nothing but s square plus 2c into omega ns plus omega n square equal to 0. So here we find that the characteristic equation in S is quadratic and accordingly its roots can be easily obtained. So writing down the roots of the characteristic equation, we have the two roots given by s equal to minus c into omega n plus or minus of omega n into square root of c square minus 1. Now let us introduce three systems based on the value of the damping ratio c. So three cases are now possible to us. One is an underdamped case. What is an underdamped case? That is the damping ratio less than or equal to 1. Obviously this indicates that the system damping is less than the critical damping. And for such a case, we can write down the root of the characteristic equation as s equal to minus c into omega n plus or minus of, obviously we know that when c is less than 1, the quantity within the square root, it will be negative, which means that s in that case can be written as minus c into omega n plus or minus of I into omega n square root of 1 minus c square. Remember, I is an imaginary quantity, that is square root of minus 1. Now the second system is a critical damped system wherein the damping ratio C equal to 1. That is, the system damping is equal to the critical damping. So if you make a substitution omega is equal to 1 into this equation, we find that we have got only a single root, that is S equal to minus of omega n. Now for an overdamped case wherein the system damping is more than the critical damping, that is very rare, C is greater than or equal to 1, in which case S can be written as minus C into omega n plus or minus of omega n into square root of omega c square minus of 1. So we find that depending upon the system we choose, we have got dedicated equations for the roots of the characteristic equation. Now we are not interested in analyzing all the three systems just because of the fact that majority of civil engineering structures, they correspond to an underdamped case. So accordingly, we'll focus only on case 1, for which the damping ratio C is less than or equal to 1. So obviously, for such a case, we know that the root of the characteristic equation is S equal to minus C into omega n plus or minus of I into omega n into square root of 1 minus c square. And here we make an important substitution, that is omega n into square root of 1 minus c square is equal to omega d, where omega d is nothing but it is the natural frequency of a damped system, right? So what does it mean? It means that the natural frequency of a damped system, we define it as omega n, which is nothing but the natural frequency of an undamped system into square root of 1 minus c square. And obviously, we know that the corresponding damped natural period Td will be 2 pi divided by omega d. So this means that the roots are now defined as S equal to minus c into omega n plus or minus of I into omega d. So if you use plus, we obtain one root as 1. If you use minus, we obtain another root as 2. Now accordingly, for the two roots of the characteristic equation S1 and S2, we can combine these two solutions in order to obtain a general solution as ut equal to a1 into e raised to minus of psi into omega n plus of I omega d into t. Remember, this is e raised to s1 into t, that's the first root, plus a2 into e raised to s2 into t. S2 is nothing but minus psi omega n minus of I omega d into t. Now let us take e raised to minus of c into omega nt outside. It means that ut can be written as ut equal to e raised to minus c into omega nt into a1 into e raised to I omega dt plus of a2 into e raised to minus of I into omega d into t. Now we know from our basic understanding of mathematics, the Euler equations can be written, which helps you to express any exponential as a series of sine and cosine. That is, e raised to plus or minus I omega dt can be written as cos of omega d into t plus or minus of I into sine of omega d into t, which means that the solution for the response of a damped free vibration can be written as e raised to minus of c into omega n into t into c1 into cos into omega dt plus c2 into sine of omega d into t. Now obviously we know that c1 and c2 are the constants which can be easily evaluated using the initial conditions, that is at a time t equal to 0, the displacement is u equal to u0 and that the velocity u dot will be v0. Now substituting these two initial conditions, we can readily evaluate C1 and C2 in order to obtain the final response as ut equal to e raised to minus of c into omega nt into u0 into cos of omega d into t plus v0 plus of a c into omega n into u0 divided by omega d into sine of omega dt. So this is the solution for the response of a damped free vibration system. Now obviously we know that this is for a damped system. So if you want to obtain the solution for an undamped system, what we need to do? We need to simply put c equal to 0. If we put c equal to 0, what happens? This term will be equal to 1. And we obtain ut as u0 into cos omega nt, because we know that when c equal to 0, omega d will be omega n. So we have u0 into cos omega nt plus v0 by omega n into sine of omega nt. This is obviously for a undamped system. And remember, this equation is exactly the same as what we have discussed in the earlier video, that is lecture 3, indicating that this equation is verified for c equal to 0. So let us make some observations out of this response, because the observations makes the sense. This is how we understand the mathematical formulation. Now look here. Sorry. If you look into the equation for ut, it is very easy to say that, number one, the amplitude of vibration, it decays exponentially with respect to time. Look here, e raised to minus c into omega n into t into a term. This means that for a damped free vibration, the amplitude of vibration decays exponentially with respect to time. For example, I have taken the analysis of this equation for one value, c equal to 0.1, that is 10% of damping. And look here, as you can see that with respect to the time, the amplitude decays. And the very important thing is that the rate of decay, the rate of exponential decay, it simply depends upon one value, that is c. That is, the larger the damping, the greater will be the rate of decay of the amplitude with respect to time. Now look here again, one more thing. Looking into the equation for ut, we find that this term is again harmonic, that is periodic with omega d. It means that for a damped system, the time required for one cycle, it is a td, or the natural frequency is omega d. So look here, I have marked the time required for one cycle of the vibration, that is nothing but it is the natural period of a damped vibration td. Obviously, we know that omega n and omega d, and from omega d we can readily calculate td, right? So just compare. I have considered another case, c equal to 0. What is c equal to 0? It is nothing but it is an undamped system. Now look here, the two variations. For an undamped system, we find that the amplitude remains constant. Whatever will be the time, the amplitude remains the same. Whereas in a damped system, we find that the amplitude decays with respect to time. So on the comparison of two terms, we find that this represents a practical system. That means every system will have some amount of inherent damping which makes that the amplitude of vibration need to decay with time, and after some time we find that the amplitude reduces to 0, right? So now let us make some more observations, interesting observations out of our analysis. Because see, in dynamics what is important is just writing down the equations of equilibrium and solving it is not enough. We need to make some observations and remember these observations, because remembering the mathematical equation is important, but our conclusion, what do we understand out of our analysis, is important. Now those two observations I have written over here. So the first observation is, what is the effect of damping on the amplitude? We have already seen that it is very critical. The effect of damping is to decay the amplitude of vibration with time. And we observed that the rate of decay, it follows an exponential form. And we also observed that larger the damping, faster the rate of decay. Therefore, we conclude that if the intent of our analysis is to obtain the amplitude of motion of a physical system, damping is an important consideration and we need to include damping in our analysis. I am repeating once again, if the intent of the analysis is to obtain the amplitudes of motion, then an correct assessment of damping is required, as we know that the damping has a significant influence on the motion. Now coming to the second one. The second one will focus on, if the intent of the calculation is to obtain the natural frequency, do we need to include the damping in our consideration? The answer is a big no. Why? Now that's what is written over here. The effect of damping is to reduce the natural frequency, because we know that the damped natural frequency is always less than the undamped natural frequency omega n, because we know that the two are related through the relation omega d equal to omega n into square root of 1 minus the c square. And obviously, reducing the natural frequency means the undamped vibration will have a larger natural period. Now remember, the reduction of this natural period is only marginal for values of damping encountered in practice. Now in order to demonstrate this, I have made a simple plot wherein along the x-axis you can see that the damping ratio C is marked, and along the y-axis is the ratio of two natural frequencies, that is omega d to omega n. That is the ratio of natural frequency for a damped to undamped system. Now look here, obviously we know that when C equal to 0, our system is undamped. Accordingly, omega d by omega n will be 1. Now as we increase the damping ratio, obviously we find that the ratio of omega d to omega n, it decreases. Obviously, because when the damping increases, the natural frequency should decrease. But however, please note here one important observation, that is the rate of change of the damped frequency with respect to the damping ratio C is very marginal. For example, we know that for many of the civil engineering structural systems, the maximum damping is of the order of 10%, that is C equal to 0.1. Now if you take C equal to 0.1, what happens? We find that the ratio omega d to omega n is almost equal to 1, which means that if the intent is to calculate the natural frequencies, damping can be neglected. So to conclude, if you want to obtain the amplitude of the system, proceed for a correct estimation of damping and include it in your mathematical formulation. On the other hand, if you want to calculate only the natural frequencies, not the response, then you can very well ignore the damping, because we find that the effect of damping on the natural frequency is minimal. So that's all about our discussion on the damped free vibrations. So it means that we have now covered fully the free vibrations, including both undamped and damped. Now in the next video, we will start our analysis on forced systems, forced vibrations. Obviously, just like the free vibration, we will have two cases, that is both an damped as well as an undamped case. Now, here I want to tell you one very important thing. People might be wondering why we are discussing too much on the structural dynamics. Remember the basic understanding here, whatever videos 2, 3, 4, etc., whatever we are discussing is only a very brief discussion of the performance or the behavior or the response of the single degree of freedom systems. And remember, this knowledge is very much required for understanding or for deriving the equations of motions for a machine foundation. And here once again I want to tell you that I have, in my personal YouTube, I have developed many videos covering, for example, idea statica, structural steel connections. There are around 40 videos, and I have compiled around 15 videos of PLAXIS, all very good videos covering shallow foundations and deep foundations. And I have also covered some very good examples using abacus. So please follow up and subscribe the channel so that you will get a notification as and when a new video is published. So that's all. Thanks a lot for listening.